Hello there and welcome to this course on feature engineering for healthcare with Python course. My name is Valentine and I'll be your instructor. In this course, we are going to undertake this structure. So we'll get started learning about the objectives of the learning experience. After that, we'll talk about what feature engineering for healthcare with Python entails. We'll talk about the most important concepts that you need to take into account and why we would want to learn about them. Then after, we'll get into a practice session where we'll get to practice how to implement those concepts using the Python programming language. And then towards the very end, we'll just talk about what would be now the next steps. So once you have completed this learning experience, what would make relevant, what would be relevant in your learning journey. So let's get started. By the end of this course, we should be able to do the following. We should be able to explain the importance of feature engineering in building accurate predictive models. We should also be able to implement various feature engineering techniques for further data analysis. We should also be able to compare and contrast different feature engineering techniques. And lastly, be able to assess the impact of feature engineering on model performance and interpretability. So what is feature engineering for healthcare with Python? This is just a process that involves creating new features or transforming new or existing ones from raw data to improve the performance of a machine learning model in healthcare applications. So just to explain that a bit more, what that entails is in the process of creation of machine learning models, we would normally prepare our data. So initially we would decide to get a raw data set that contains the data that we want to use to train our model on. And we would, initially we would just decide to train our model without necessarily looking into whether that data set fits the model, whether that data set is in an optimal format that the model can be able to learn from. So for example, we might get a historical data set that contains patients' information about whether they have had a certain disease such as diabetes or not. And we would probably be intending to create a machine learning model such as maybe logistic regression, to be able to classify whether newer patients are likely to have diabetes or not. So in order to ensure that that data set is in the right format, we would need to ensure that we adhere to what logistic regression would normally assume about the data that it's trained on. So for example, we'd need to ensure that the independent variables, those are the features, they're not correlated. So that would mean going into the data set and looking at that data set a bit more closely, performing statistical techniques to determine that correlation between the different variables. In addition, we might decide to also create new features from existing ones. So if we have some data like height, age, weight, we could end up deciding to create a new feature such as BMI that the model can learn from and be able to use to classify or to be a bit more accurate when it comes to predictions. So generally, feature engineering is just a way of improving models' performance. So initially, assuming that you created just several models, you realize maybe the logistic regression has 85 in terms of accuracy, 85%, 0.85. And our metric of success, or we would want it to, we would want a model that performs with an accuracy score of 0.9, that's 90%. Then we can perform feature engineering which just entails looking at the data set, the training data set that you had, and making it better, and for the model to be able to effectively perform better. That's usually one of the ways we can improve our models. The other way would be to perform what is called hyperparameter tuning, which is to look for those optimal values of hyperparameters, because models usually have hyperparameters, which are just like settings, and we can then determine those optimal hyperparameter values and then use them for our model. So those are the two ways that we can be able to improve a model's performance. Aside from that, if we are not able to improve our model's performance, the other alternative is usually just to look for a different model, maybe an advanced one. If you don't get to that metric of success that you want, or you could decide to change the research question. All in all, again, so this process of feature engineering will just involve performing various techniques on your features. These are the independent variables that you would later onwards use for the model that you want, and it's usually much more specific for when you're training. When you're performing feature engineering, you would be training, you would be preparing that data set for a particular model, not for all models, because different models have different assumptions about the data that you're going to be training it on. So this process is critical because, again, healthcare data can be complex and high dimensional. You can have lots of variables, and you might just want to work with the most important ones in your analysis. And not only that, you tend to have different types of data. So in an effort to ensure that you have the right type of data for your model, you then perform feature engineering. A use case might be, we could use feature engineering techniques to transform raw electronic health record data, such as patient vitals and medication history, which we can later use to create a machine learning model that predicts detection of sepsis. So that's just one particular use case of feature engineering. In terms of, this shouldn't be reading clustering, this is just benefits of feature engineering. So in terms of benefits, what you get is improved model performance. Once you have a data set that you've transformed through using feature engineering techniques, so you have a better performing model. You also have reduced overfitting, which just refers to the fact that the model does not just learn from noise from data. It now gets to learn a bit more from the patterns that are meaningful within your data set. Enhanced interpretability. You're able to create new features which make it easier for you to be able to understand why a model performs better. You might realize that when you're performing feature engineering techniques, there are set features. There's, of all the features, there are a particular number of features which tend to perform better than the other, which indicate that the model itself has been highly impacted by those variables or features that you would determine that they actually lead to better performance. Dimensionality reduction. This just refers to reducing the number of features that you're working with. So you could perform dimensionality reduction techniques, which tend to you can have maybe 100 variables, but if you perform dimensionality reduction in your data set, you might decide maybe to have only 10. That again reduces what is the feature space, and also it allows you to use less computing resources during your training process. Yes, and you spend less time as well. And I think what I've already talked about is just the identification of key factors, of key variables within your features, you're able to identify which variables are most influential in affecting the variable of interest, which would be the target outcome. So yeah, so that's just a quick bit about the benefits that you get upon performing feature engineering. These are the feature engineering techniques that we're going to be performing. These are just categories, but under each you get to perform various techniques. Like encoding just means to convert categorical variables into numerical representations. So maybe a column like age or smoking status would by default have categorical data. So they'll have data that's in textual format, but it's in classes or categories. So like, for age, you'd not even age, so for gender, sorry. For gender, you might have something like male, female. Those are just categories. So we would perform, various encoding formats to be able to ensure that the data itself is in a format that can be consumed by a model. But again, there are various encoding techniques that we can work with. And we would essentially test on their impact on how the model performs. So if we haven't gotten to a metric of success, we could always decide to try a different type of encoding technique to see what happens, to see the effect on its performance. Feature scaling just ensures that our data set is the dataset values are within a particular scale that we would want. Daytime feature extraction would refer to the fact that we would extract features such as day of the week, time, seconds, from just date time data. So if you have just one column that contains date time, we might be able to extract maybe 4, 5, 6 other features from that just one column, which would represent maybe the year, month, day of the week, could represent hour, could represent minutes, time, or seconds, etc. Feature construction just refers to being able to create new features out of existing features. Like we can create BMI out of other existing health-related data columns. Feature selection would involve performing techniques that test a combination of features on a model, and they check for the accuracy scores and see which of the features perform better or will lead to better model performance and which one do not. And then they would recommend the ones that lead to better feature performance. Skewness reduction just involves ensuring that your data set, the variables that you have, are more towards having a normal distribution. So, models such as linear regression or even logistic regression usually assume that the data you have, the variables, have a normal distribution. So in many cases, you might want to perform techniques related to skewness reduction. Dimensionality reduction involves just being able to reduce the number of features into a lesser number of features, which would again represent those large number of features, and you just have what are called components. So that's what we're going to be covering in this workshop, hoping that once you've gotten to learn about those techniques, you can be able to apply them in real life cases when you're working on machine learning problems and you need to improve your model's performance. It could be maybe in a healthcare context where the stakes are quite high, so you're required to have a high performing model because of the fact that when the model performs poorly, there is so much that you can be able to lose. Same case in the finance industry, and also in machine learning competitions, where also the metric of success is how accurate your model is. So at this particular point, I'm going to ask you to visit the link that is in the video description. It should take you to a page that looks like this, where you can be able to get the sample practice resource, and we can get started working on the sample, on the practice work. So this will be the document that you'll be able to access, and we can be able to use this for working. If you're an Afterwork member, consider the practice notebook. You won't get the sample. The sample has fewer challenges, but the practice notebook has a variety of challenges. And also feel free to pause the video whenever you feel like you need to perform a task that we have demonstrated. So yeah, pause the video. If you feel like we are too fast, you could always rewind because this video is being streamed. So yeah, let's do that. Get to the sample notebook, or the practice notebook. I'll be using the practice notebook, still the same. Has different sections. So the first thing that we're going to do once we get here is to save a copy of this notebook. So go to File, then Save a Copy in Drive. Just note that you're doing that on your sample notebook. So File, then Save a Copy in Drive, and it should open a new copy in a new tab, and then you can use that for your work. All right, I'll just use mine in playground mode. I don't want to make changes to the notebook. All right, so getting started, starting off, we'll import our two standard libraries, Pandas for data manipulation and NumPy for scientific computations. Let's import them by clicking on that icon, this icon, and also this other icon. It should take a few seconds to have the notebook connected to Google servers, and then you should be able to import them. So check. Okay, you're good to go. All right, let's now go through encoding features, techniques. So there are various encoding techniques. So encoding just refers to just getting a representation of a numerical representation of the values that you find in a categorical variable. So there are various encoding techniques. So we'll get to learn about just three of them. Label encoding is the first one. So this is a method that we can use to assign a value. So assuming that we have a feature called color, so color column that has these values, red, blue, and green, we can use label encoding to just assign just randomly, without any, actually the first value that it finds, the label, this technique in your categorical variable will just be given the value 0, the second one value 1, the third one value 2. If there are 10 different categories, it will create just to assign values from 0 to 9. So yeah, so let's import the data that we need for this case. So we have this data set, patient data set, and what we want to do is to perform label encoding on gender column, so this column, on blood type column, on this column, and also on insurance type encoder, so on this other column. We could also perform the same case on diagnosis, medication, hospital, if we wanted. But just for ease of learning, we are going to perform label encoding on those columns. So we're going to replace the values, the categorical values with their equivalent representation. So we import the label encoder class, which is what we're going to use for this case. And then once we have imported it, we create what are called just instances for each and every categorical variable that we want to replace values for. We are going to create what is called an encoder. That is the one that's going to go through the values within the categorical variable and then create the respective values. So for gender encoder, we would need to create, it will go through the entire column and get the and determine how many categories there are, and also now get the numbers for each category. So for gender encoder, we do that. We also do that for blood type and also insurance. And then we use the fit transform function to be able to apply now this technique, label encoding. So we are going to replace the respective categories with their numerical representations. For male, we'll replace it with 0, then female 1. So the same case we do with blood type, and then we also do it with insurance type. And then we just display the first rows of the data frame. As you can see, actually, we have gender replaced. Actually, it gave male the value 1 instead of 0, and female 0. And for blood type, we have O negative as the one that gets a 7, A positive a 0, etc. So so that's what it was able to do. And we could have done it with the rest. So at this particular point, I'm going to ask you to apply this technique, label encoding technique, in this challenge. So you're going to work on this challenge. Just write your code in this section. So you're going to just apply label encoding on just one column. If you want, you can, do the same case for other columns as well. If you're an Afterwork member, once you've completed, just go to the solution notebook and confirm your solution. Moving on, so here we are just representing, we're just replacing with numerical equivalence. We can also still do the same thing, but now take into account some sort of order. So assuming that we know that, let's say in our case, I think, okay, maybe a better example would be what we have here. So assuming that we would want to assign maybe a certain value within a data, within a categorical variable. So for example, we want to assign, cholesterol level. We want to assign the value high. It's an equivalent representation of the value 3. Then normal, we want to give it maybe 1. What would be a good one? I think we can use this one. So we might want to decide to assign, just trying to look at what would make sense in our case. Negative, positive. Okay, so I'm looking at this and I'm trying to understand what would be better. So assuming that we decided to assign, maybe if there is a negative, we want it to be a 0. If there is positive, we want it to be a 1. Or in some other cases, you might have values in a categorical variable where you have low, medium, high. So you might want to assign low to be a 0, medium to be 1, and high to be 2. In such a situation, you also want to take into account of another factor, not just assign any value to just any categorical value. You might want to have that particular order. So to be able to do that, we can use what is called, we can define our mapping, or we can define how we would want to replace those, to have those categorical values. So we can use a dictionary. So we say maybe for this value former, we wanted to have the value 0. For current, we want to have it the value 1. For negative, value 0. Positive, 1. So the idea here would be that we are also trying to tell our model something about the categorical values. So we want to also tell it that it should also take into account of the order of values, not just the value itself. So for former, we want to assign it the value 0. For current, the value 1. For negative, 0. For positive, 1. So in any case, let's say for smoking status, the value former will be replaced with 0. But if you use maybe something like a label encoder, you might find this former being given the value 1 instead, which might not be what we would want. So technically this tells our model that order of the values it's important, and it will also get to take into account of that. So we use the map function to apply or to perform the replacement of the respective values that we've identified. So former, in any case we have former, it will be replaced with 0. So that value, same case current 1, negative over here, 0 and positive 1. And then we apply the same for smoking status. We also do the same case for diabetes. We also do the same case for heart disease status, which is the one that you see here. And we could also do the same thing for this particular column, cholesterol level, if we wanted. So yeah, so let's perform that type of encoding. It's called ordinal encoding. It takes into account of order within your variable. So there we have it, so smoking status, diabetes status, and cholesterol level. All right, work on the challenge and then we can continue. Moving on, by the way, you can pause the video. Don't forget to do that. Moving on, one-hot encoding. So in those two techniques, we've been replacing technically the categorical values with just the numerical equivalent. So this is a new other type of encoding technique that we can use, and it usually creates what are called binary columns for each category, where if you have a category, let's say called gender, and you have male, females, you would end up having two new columns that represent gender, gender male and gender female, and the values of those respective columns would be either true or false. Technically, the new columns that you would create would be dependent on the number of categorical values that you have in a variable. So for gender, let me just run this. You would end up creating, so gender, we have male, female. You end up creating two binary columns, one called gender female, another one called gender male, and their respective values for, say, gender female would be true or false. And the idea is that whether this particular record has gender female as true or false. So generally, these are just binary columns that you'd create. For other columns that probably you have more than two categorical values, you then have as many new binary columns as you'd have the categorical variables values. So something for blood type, if you have 7 different categories, you'd end up having 7 different binary values. So for example, you'll see for blood type, we'll have blood type O positive or negative, etc. So how to apply this technique, one-hot encoding, what we do is we would use the getDummies function, and we pass to it the data set that we want to create the new binary columns, and we specify the binary columns, and we can now display now our data. You'd then need to delete the old names, the previous records. Let's say for blood type, you'd need to delete. You don't need now the original one. You now work with the new values. So for example, for gender, you can see here we have gender female, gender male with true, false. So it just checks whether for this record was gender female, did it have a gender female value? So if it did, then true, which it did. Then for gender male, it's false, etc. So we'll do the same thing for all the other columns. In this case, we get now as quite a large number of variables, which might tell our model something. You never know. But again, once you get many variables, you could always decide later onwards to apply another feature engineering technique, like what is called feature selection, to determine which actual features are important, or alternatively, you could also reduce the number of variables that you're working with. All right. At this particular point, pause the video and then work on the challenge. And then once you're done, we can continue. Feature scaling. So feature scaling generally entails ensuring that the values that you have within your data set are within a particular scale so that a model does not learn too much of one variable. So for example, we could perform what is called standardization, which ensures that we rescale our values and have those values have a mean of 0 and a standard deviation of 1. So assuming this is the data set that we would initially have, we would need to scale the numerical variables. So the one that's not numerical would be gender, blood pressure, or even patient ID. We wouldn't need, it wouldn't provide meaningful information for a model. It's just an identifier. Gender, we would exclude that. Blood pressure, we could decide to split the values and have 2 new columns, but for now we will just exclude them. So what we are going to be applying our feature scaling technique, that standardization to, would be age column, height, weight, cholesterol, glucose, heart rate, as well as exercise hours. That's actually what we're doing here. We want all these variables, numerical variables, to have a mean of 0 and a standard deviation of 1, so that values like cholesterol are not, and height do not have a significant effect, too much of a significant effect, so that our model doesn't learn too much, as opposed to something like exercise hours. So how we do that, we import the standard scalar class, and then we create an object of it, and then we use its fit transform method and select the columns that we would want to perform feature scaling for. Perform feature scaling and save the result in data scaled. And here we're just displaying our the data for that particular. We actually here we are replacing the scaled data with now the previous data that we had, and we are displaying now the new data set that we now have. So you'll see that now we have new data that we can use. I forgot to put cholesterol in here, so you can also add it here. That's why you see we have 200 in our case here. So yeah, so the data is, when you look at it closely, there isn't any numerical variable aside from just cholesterol that has a significant deviation from the rest of the variables themselves. So they all have a mean of 0. Yeah. So, and also a standard deviation of 1. At this particular point, pause the video and then work on the challenge. Another technique, still feature scaling technique that we can use aside from standardization, would be what is called min-max scaling. So a min-max scaling would scale our data not to have a mean of 0 and a standard deviation of 1, but to be within the values 0 and 1. So it would subtract the minimum value of that particular feature, then divide it by the range of the feature. That's maximum minus minimum. So yeah, so let's do the same with now this new data set. This is just the record for the premium. Sorry about that. I think I had not correctly put that. So let's have a look at this. So when you look at it closely, you'll see that we can be able to do our feature scaling on these records, the ones that I'm highlighting. So we would import the min-max scalar, not the standard scalar. Then we would create an object, then use its function to apply the feature scaling technique to these variables. Then we preview the outcome. So in our case here, we will have all those records have values between 0 and 1. Awesome. At this particular point, pause the video and then work on the challenge. Last type of scaling technique that we will get to learn is what is called feature robust scaling. So this uses a different approach when it comes to scaling our features. So it usually would scale them such that the features are not affected by extreme values. And the idea is that if you have outliers within your features, it uses a technique that ensures that those outliers do not significantly impact the performance or the performance generally of our feature. I can see I had not included the technique there, but let me see if I think it's also it's in the challenge. Yeah, so I think it's actually what I had here. I did it vice versa, so I removed the challenge for that. But yeah, so how we import the data, how we perform feature scaling is to we're using robust scaler would be to use the robust scaler technique. We would import it, then we use its fit transform function, and we apply it to the column that we want. We just wanted to apply it to one, but we can apply it to multiple. So just copy this, paste it here, and let me run this. So I can be able to use it on any numerical column that I want. So if I display this, I should be able to see that the height column has these new values, which are not really affected by the extreme values, its extreme values. So I can do the same thing for those other columns. You can attempt and do the same thing, apply the same robust scaler technique to all the columns that you have, and also work on the challenge. All right, moving on, date time feature extraction. We can also decide to extract features from specific date columns. So for example, in our case over here, we have this data set that contains date of birth, admission date, and discharge. These are just date columns. They contain just date values. And what we are going to do in order to work with date data, we would need first of all to convert it into what is called a date time format. So we use the to date time function to convert date of birth column to a date time format. It's more like how we would convert a numerical variable. Before perform mathematical operations on that numerical variable, we would convert that numerical variable into a numerical data type. So it could be an integer or float. So here we are converting our data into a data format. So which into a date format, which is what we are doing here for these three variables: date of birth, admission date, and discharge date. And then once we do that, we then extract now a days, which is 01, or month, say would be now in our case maybe 09, or year, which is 2021, and create new columns out of those particular days. So in this case, we are creating 3 columns out of the date of birth column, and those 3 columns will be called date of birth day, date of birth month, date of birth year. We also do the same thing for the other dates: admission date and discharge date. We create 3 new columns. So essentially, we have 9 new columns that we can use in our analysis. So if I run this, I should be able to see now on the far right. So we still have the old ones. We can still remove them if we want. And we can see that here, date of birth day, 15/7/1985, which is what we had here, 15/7/1985, which is what we have here. And you can also extract further information, not just these 3 pieces of information. You could also extract like day of the week. Was it a Monday or Tuesday or Wednesday? You could, if you had even something like time information, you could also extract even hours. You could extract also minute, second. You could even extract whether it was afternoon or morning. yeah, so there's so much that you can extract in terms of features, and those features might be useful in helping your model learn a bit more about what each record entails in terms of its characteristics. So whenever a new record resembles much more that record, it's likely to be given maybe a value that's closer to what it has learned from. At this point, pause the video and work on the challenge. Calculating elapsed time. So sometimes you might also decide to create a new feature that it can be derived from existing features. Like for example, we might be able to determine, let's say, how many days a patient spent in a facility by simply. So if I load this data set, where I can calculate the difference between discharge and admission date, and I can know how many days a patient spent in a hospital, and I can create a new column that contains that information. I can also do the same case on creating a new column on medication end and medication start, and I would know how many days the patient has been on medication. So yeah, those are just new features that you can also create pertaining to patient, etc. Pause the video and then work on the challenge. All right, feature construction. So this actually involves what we've been doing, creating new features out of existing features. So we might decide to create maybe a new feature based on what we understand about a certain domain. So for example, if you look at this data set, we might decide to create a BMI feature out of the weight as well as the height data that we have, because there's a formula that we can be able to use for that. And that's what we do here. And we create that new column, and we might also have maybe some other understanding of maybe some other important factor, which is called maybe a risk factor, that we can derive from cholesterol and heart rate. So we are multiplying the values of cholesterol and the heart rate. Here we are, this 2 squares just means raised to the power of 2. So data height column value divided by 100 raised to the power 2. So that's what we do here. So if you look closely at the very far end, we have BMI and risk factor values. So those can be something a model can also get to learn more about. Again, not only a model, by the way, you can also, you yourself, you might get to uncover new insights based on what you're doing in terms of analysis. Pause the video and then work on the challenge. Reducing skewness. So sometimes you might want to have a variable not be quite skewed. So maybe if it's skewed to the right or left, we might want it to have some sort of to have values which are much more normal. So to have a normal distribution. So we can be able to apply various techniques which would apply just some sort of transformation to each data point, and you can be able to get the normality that you are looking for in terms of having when it comes to your data distribution. So for example, in our case, we might decide to use log transformation, which is another technique that we can use which is a technique you can use to reduce skewness. So what it does, it applies what is called a natural logarithm to each data point. And we would do that. Let me reload this new data set. So we have age, weight, height. We would actually do that for the numerical variables. So for example, we would apply this function. We would use the apply function and use what is called a lambda function, which would apply our natural logarithm, which is represented by log of now whatever value that we want. So we use numpy, and the function from numpy we get is log, and then we pass the value of the current data frame column value to the log, and that would give us the equivalent log value for that particular column. That's what, for that particular value in that column, then we replace that. Then we create a new column called log of that. The same case, we do all the same for the other values. For blood pressure, you could have excluded it, but we also decided to just split the value and get the first value and apply that, in the same case with the second value, and apply that, and then merge them together later. So what we end up having are just now values which have just log values, and if I display that, create a distribution, a histogram, I should be able to see that I have I have variables. I have just variables which I've created, which are closer to normal, and you can compare them. Let's say for age and log of age, when you look at age, was skewed on one side, but you can look at it as one that's not that it's actually this one. It's not too skewed to the direction that it was. And when you look at maybe something else like, let's look at, what can we look at? Actually, age is which one? Age is this one. Yes, age is this one. Because the top age, weight, height. Yeah, height also looks a bit more like it. Yeah, so that's what you can use. You can now use that in your model. And models such as logistic regression and linear regression tend to have this assumption of normality. And the other type of technique still, by the way, you can pause the video and work on the challenge and unpause when you're done. The other transformation technique that we can use aside from log, we can use what is called a box Cox. It allows us to be able to also normalize any sort of non-normal data by applying what is called a power transformation. So, and we can be able to do that by simply using the, we import a SciPy library. It's another library that's it's an advanced scientific computations library, provides us with various scientific techniques. So we use the box Cox function from SciPy, and we apply it to the column that we want, and we would get, so for example, the demonstration, we apply it to the weights column, and this is what we get, and we can display the distribution initially and after. So this is what we had before, and this is what we have after after the transformation. You'll note some slight difference, not a large difference, just some slight difference. All right, pause the video and then work on the challenge, and then we can continue. Feature selection. So in some cases, once we have the number of variables that we have, we've prepared our data from just those other techniques, feature engineering techniques that we've performed, we might want to determine which features impact our model performance most, and we can use what are called feature selection techniques. There are quite a number of them. There's recursive feature elimination, there is forward selection, there's backward selection. There are quite a large number of them. Not a large, there are a few, several, but I chose to just showcase this one, which allows us to be able to determine those variables that impact the model's performance. So it's called recursive feature elimination, which is a feature selection technique that allows us to be able to do what is just removing variables and building a model on the remaining variables during model creation. So this technique would allow you to build several models, but then again, at the same time, be able to, for each and every model, remove attributes and check how that removal of the attribute or the column or the variable has in terms of an effect on the performance of the model. And at the very end, it would give you the respective performance of that model. So in our case, we are going to work with this data set. We can decide to just work with just a few. Can decide to work with age. We would want to work with heart rate, temperature, weight, and yeah. So assuming that those are the ones that we would want to work with, we can then again, we could still also work with more. This is just an assumption. Those are just 4. We might want to decide to use maybe a random forest classifier to build that, but we want to select the best performing features, 3 of them. We can use the RFE class from sklearn class. So we also import our random forest classifier. And then we use RFE and the instance of our model, and then specify the number of features to select, the ones that perform best. And then we use the fit method, and we select now the features that we want. We display the features that we want, that we would want to use, which are the ones that would perform best as shown here. So if we run this, we would end up getting age, heart rate, and weight. Out of the ones that I mentioned, age, heart rate, temperature doesn't isn't the best. Actually, it seems temperature doesn't impact as much in terms of our model performances as these 3. Yeah, so that's it. You could try that with just different other problems that you might be having in your maybe work or in other past workshops. At this particular point, pause the video and then work on the challenge. Once you're done, we can now wrap up. We can go towards we can work on our last concept, dimensionality reduction. So assuming that you have a large number of variables and you want to just simply reduce them to have maybe just a few, you can decide to use what is called a dimensionality reduction. So it just reduces the number of variables to just a few. So if we have 100, we can reduce them to 10. Those individual 10 variables would be representative of the large number of variables. So in our case, we can use a technique like what is called principal component analysis, which would transform our data into these new variables, which we can call components. So by that, we are able to reduce on the number of variables. There's a situation that's usually called the curse of dimensionality, where some models of a type of algorithm would perform poorly as the number of variables increase. So dimensionality reduction would help us to avoid that curse of dimensionality. It would also help us be able to reduce computational complexity and also reserve the amount of computational resources that we have. So we'd end up with, using lesser resources, and we do improve our model performance by just removing redundant and irrelevant features. So in such situations, we have components which are effective. And again, once you perform still dimensionality reduction, you could always perform feature selection techniques to determine which values or which variables or features perform better, and you can always drop components which seem not to contribute towards model performance. So how we perform that, we can use the PCA class from sklearn, and we select the features, assuming that we would want to technically even this is not supposed to be there. Why I should have because why we are not working with the target variable. Even you just select the features because that's what we would want to reduce. So we drop anything else aside from ID and blood pressure. So ID and also blood pressure. We could decide to split this again also into different columns, but we just decided to drop them. And then we use the PCA class. We create an instance of the PCA class, an object, and then we specify the number of components that we would want. And then we use the fit transform function from PCA to apply the transformation to perform that operation for principal component analysis, or to perform dimensionality reduction. We store our components in this variable, and then we print it out. And this is what we have. And we can use this in our model and train it as training data. At this particular point, pause the video and then work on the challenge. All right, so if you're an Afterwork member, again, you can always consider just reviewing your solutions and using the solution notebook for that. And if you're also not yet an Afterwork member, you can always consider becoming one, and you get access to all the resources that we have on our platform. So that's it with regards to our learning experience so far for this workshop. In terms of next steps, once you've gotten to learn how to work on feature engineering techniques, you could decide to maybe focus a bit more, maybe get to learn more about maybe more of dimensionality reduction or feature selection. Or alternatively, what you might end up deciding to do is to now move towards learning newer techniques that would help you to have a better performing model. You could decide to learn about hyperparameter techniques. These are just techniques that allow you to tune what are model parameters. Alternatively, you could also get to learn about ensemble learning methods, get to learn about advanced types of algorithms that you can use to create machine learning models. Maybe you've heard of XGBoost, CatBoost, AdaBoost. Those are those ensemble algorithms that might end up performing better than the normal machine learning models that we normally work with, the likes of linear regression or logistic regression. All right, that's it with regards to this learning experience. If you experienced what you wanted, so you were able to achieve the learning outcomes, and you feel like you learned a lot, and you'd want to tell us that we're doing something good, that we should keep on continuing, we should continue having such learning experiences, be sure to give this video a thumbs up. Just be grateful for that. And if you'd want to be informed when we post such learning experiences, be sure to subscribe, and see you in the next